Alright, example number 9. We have the plates of a parallel plate capacitor are 5 millimeters apart and has a surface area of 2 meters squared. The potential difference of 10 kilovolts or 10,000 volts is applied across the capacitor, and we're asked to compute the capacitance, the charge on each plate, and the magnitude of the electric field in the region between the plates. Let's start writing down the given here. We have the distance between the two plates is 5 millimeters, which we'll want to convert that to meters. So that's 5.00 times 10 to the power negative 3 meters. The area of the plates is 2 meters squared. It's already in meters squared, which is nice. And the voltage is 10 kilovolts, which is really 10,000 volts. Okay, in part A, we're asked to find the capacitance. Now, the capacitance can be calculated in two ways. We have the physical characteristics of this capacitor. It has a sort of a distance between these two plates. Here's one plate that's positive, another plate that's negative, and each of these plates have a sort of a cross-sectional area in here. And here's distance d, and there's the cross-sectional area. So we can calculate the capacitance of this capacitor by just knowing the cross-sectional area and the distance between the two plates, which we're given. So let's go ahead and substitute. Our permittivity of free space is 8.85 times 10 to the power negative 12 farads per meter. The area is 2 meters squared, and the distance between the two plates is given as 5 to the power negative 3 meters. Alright, using your calculator, you'll get an answer of 3.54 times 10 to the power of negative 9 farads. That's quite a small unit of capacitance, so we can rewrite this in terms of microfarads or even picofarads. Let's do this in microfarads first. If we were to convert this to microfarads, we know that 1 microfarad is equivalent to 1 times 10 to the power negative 6 farads, which will give you 3.54 times 10 to the power negative 3 microfarads, or I suppose you could write it as 0.00354 microfarads. Or alternatively, you could write this in picofarads. If you were to take this 3.54 times 10 to the power negative 9 farads, then multiplied by a picofarad, which is 1 times 10 to the power negative 12 farads, you will get 3,540 picofarads. In many applications, the most convenient units of capacitance are in the microfarad or the picofarad that I've just written down. Okay, now let's calculate the charge on the plate if it were raised to a voltage of 10,000 volts across these two plates. So we know the capacitance is not going to change. What will happen is the voltage will change as the charge changes, or the charge will be directly proportional to the voltage. So more voltage, more charge. So the relationship between the capacitance and the charge and the voltage is as such. Capacitance equals charge divided by voltage. So therefore, the charge of the capacitor, this is the charge of either plate. So we have one plate that's positive Q and the other plate that's negative Q. The charge of either plate would be equal to that capacitance multiplied by the voltage. So let's go back to this capacitance in farads. So 3.54 times 10 to the power negative 9 farads. And then we're going to multiply this by the voltage of 10,000 volts. And this gives you the value of 3.54 times 10 to the power negative 5 farads. Once again, you can see this is a very small amount of charge, and so it would probably be more convenient to write it in microcoulombs. So we could convert this to microcoulombs by taking 3.54 times 10 to the power negative 5 farads multiplied by 1 microfarad divided by 1 to the power negative 6 farads. And this gives you a charge of 35.4 microfarads, which is commonly used for charges. And the last part, to find the electric field strength, we recall hopefully that the electric field strength is equal to the voltage across the plate. So this should really be thought as a delta V, but we write just V, and hopefully you remember that as the change in potential from the positive plate to the negative plate. all right, divided by the distance between the two plates. If you're going to use the potential drop between the two plates, then we need to know the distance between the two plates. And technically, there's a negative in here. And the negative is only really there to indicate the direction of the electric field. Whereas you move in the direction of the electric field, which is from the positive to the negative, the electric potential will drop. Anyhow, substituting our voltage, we have 10,000 volts, and the distance between the two plates is 1 times, oh, not 1, actually 5 times 10 to the power of negative 3 meters. And this will give you E, the magnitude of E, to be equal to 2 times 10 to the power of 6 volts per meter. And that's it for this problem.